Welcome to qnawire.
Alright, so this is a one-dimensional kinematics problem. Let's just go ahead and write down in mathematical form all of the information we have. So we know that Darrell Griffith attains a height of 1.2 meters as his final height. He starts from the ground, so that's an initial height of 0. By definition, his the velocity or the speed he's going at when he reaches the final height must also be 0. And we know that the acceleration is going to be given by the acceleration due to gravity. So the question is, what initial velocity did Griffith need in order to attain that height? So we're going to want to use a very specific kinematics equation. That's the one that doesn't involve time, because we know nothing about how long it took him to get there. So that one involves the square of each of the velocities being added to 2 times the acceleration times the change in height. So thankfully we know that final velocity is equal to 0. So we can go ahead and put a big 0 over there, and then start plugging in a couple more values. So we know the initial velocity. We know that the acceleration due to gravity was negative. And that's our final height over there. So now we just rearrange things, take the square root, isolate b naught, and get that it is the square root of 2g yf. Yes. So now we can plug in numbers and see that that's equal to 2 times 9.81 multiplied by that 1.2 meters, square root everything, then get that his initial velocity must have been 4.9 meters per second. Alright, so that's part A. In part B, we want to know that if it took him 0.3 seconds or 300 milliseconds in order for him to give himself the oomph he needed to jump that high, how fast must he have been accelerating himself in order to accomplish that? So we're going to need to, of course, recycle our answer from the first part. We do know that now we're considering to be the final velocity is 4.9 meters per second. He started from west. What acceleration is needed in order to accelerate into that height? So we have this acceleration right here, and then just using the definition of average acceleration, we have delta v over delta t, which in terms of how we wrote it is vf over delta t, and then plug in those numbers, and then specifically to many significant figures, about 4.852, 0.300 down here. And then we get that the acceleration must have been 16 meters per square second. Cool. And then lastly, in part C, we want to know what force the ground was exerting on Darrell Griffith over that time interval. So in other words, what is the normal force? So let's go ahead and draw a little free body diagram. So of course his weight is pulling down on him, that's mg. And then this is where Darrell Griffith is. Then we definitely need to make sure that we're drawing the normal force as being a longer vector than his weight, because he's going up, so it has to exceed his weight. So that's what the free body diagram would look like. Our net force is going to be the sum of the forces that are acting on him, so that's the normal force, minus the weight. So that's the answer to that question. And then lastly, we're going to go ahead and finally calculate that net force. So using Newton's second law, we know that the net force is going to be equal to his mass multiplied by his acceleration. We are not given his mass explicitly, but we do know his weight, so we can calculate that by substituting in W over G. Plug in some numbers. We're told that his weight is 890 newtons. and multiply that by acceleration, which we saw was 16. And then acceleration due to gravity is 9.81. So his net force must be 1,500 newtons, just two significant figures. And then lastly, to wrap off the question, we need to know what that normal force the ground is exerting must be. So we can find that right here. We're getting that normal force is equal to the net force plus his weight. And then just literally add those two numbers together to get 2,400 newtons to two significant figures. And then we're all done.